many of you guys know, I do a little internet sleuthing. I don't understand why people don't block me. Not the first time, but I get potential students, want to see, will they fit well in the lab? So one of the first things that I always want to try to see if there's any evidence that the students love animals, because that's what we work with in our group, and so we want to make sure that they'll be treating the animals with respect. And from a young age, there was some photos of her with horses. She worked with sleuths. She fostered dogs. She had a cat that she adopted, a street cat, and she even tattooed an animal on her skin. So I was like, okay, pretty good evidence that she likes animals. How about, does she like the ocean? Also found some evidence that she was into scuba diving. I know I'm pretty good at finding things. I think she's probably in junior high at this point. You can't really tell. I really still don't understand why people don't block me. I do try to pick photos that are not too embarrassing, but she also pretended to be a shark on some 8th grade field trip, I think so also. There she is right there. And she is a diver, so I was like, okay, she clearly, from a young age, has shown an interest in the ocean, and she also has ocean scenes tattooed, so again, figure anything that permanent has to be an interest. I was interested in finding out if she had any computer skills. I didn't find evidence that she did, but her cat clearly did. So, and then I was accepting her during COVID, and so it's really important that students were flexible. So found some evidence that wasn't really the flexibility I was looking for, but figured it could be useful. But all joking aside, I was happy when Kaylee joined our lab. She's been a valuable team member, and at this point, one of the reasons I had to do so much internet sleuthing is because she is very good at avoiding photos. She's kind of like a ghost, or hides from the camera. But despite having trouble finding pictures, I did find a few. She really helped all of the students with different projects. She was an important member of the Stranding Network. She helped with sea otter observations. Even though Sierra didn't have any photos, she did share some fun stories about getting stuck in the mud and how she very much appreciated Kaylee's positive attitude. She's helped with elephant seal work, and she's done a lot of teaching. So this is one of our class field trips, and she's TA'd twice for me and 4 times at CSUMB. I think that's right. She's also a dedicated volunteer, so she worked for sleuths through most of her time here, or a lot of her time here, and then when that ended, she started volunteering at the Marine Mammal Center. She's been a really valuable team member. She's been a great friend to everyone in the lab. She participates in all of our lab functions. Here's the fun ones, not the pictures of lab meeting, those aren't as fun. But she's always giving valuable feedback to the other students. And always, like I said, helping them with their projects. She's presented some of the preliminary results at 2 different venues, the CSU Coast Annual Meeting and the CSUMB Grand Slam, and then also some smaller things. And then she has received several awards during her time here, including the First Generation College Student Award, the Cole Persky Memorial Scholarship, and the WAVE. And with that, I will let her take over so she can tell you what she's been working on for the last few years. She can stay right there. All right.
So these are temporary animal-born data loggers that collect a variety of data types, including positional, physiological, and environmental data, which we use to study things like animal behavior, physiology, ecology, and habitat use. And in particular, they're really critical for marine animals that spend the majority of their lives at sea out of easy view of researchers. So in order to study these animals, we may place one or more biologgers on a single animal, which I'm going to refer to from here on out as a biologger configuration. So now, understandably, when we place these data loggers on animals, there is a potential that they could impact the animal's behavior. So they're vital for data collection, but they can have species-specific direct or indirect effects. Those can include things like stress from capture and handling. They could be short-term effects on movement and energetics, or long-term effects on survival and reproduction. And then, of course, if the animals alter their behavior response relative to the biologgers, this can lead to research artifacts in our data that do influence the representativeness of the data. So it's important to periodically investigate what kind of impacts there may or may not be, just to understand whether, or just to protect both the animal's welfare and the integrity of our data. So on marine mammals and penguins in particular, there has been some work, quite a bit of work done on looking at the effects of biologgers, since we rely so much on these instruments to understand them. And some of those impacts that have been detected are things particularly associated with dive behavior and foraging success that include increased or reduced foraging, reduced mass gain associated with that, but also changes to bottom time or dive duration. In some cases, they had shallower dives, or they had longer foraging trips, or on a very fine scale, they had reduced swim speed. And so we do have current guidelines addressing some of these impacts, but they're predominantly used or based off of terrestrial animals, and they are mass specific and sort of require that biologgers be no more than 5 to 10% of the animal's mass. However, for marine animals, drag is more relevant in water than mass typically, but it can be harder to measure, and so that kind of necessitates the use of drag proxies. The other aspect of this is because we almost exclusively rely, or not exclusively rely, but because we rely on these biologgers for a lot of data for these animals, it's hard to have a control group since you can't really get data off of an animal that doesn't have a biologger attached to it. So it does present some additional challenges. And so as a result, we do have some good recommendations for use of biologgers on marine and aquatic animals, but for marine mammals in particular, there isn't a definitive guideline like there is with terrestrial animals. That said, those recommendations are fairly comprehensive and do include suggestions to optimize design to minimize the footprint of the biologgers, to maintain or minimize the frontal area, and to adjust their buoyancy as needed. They also have recommendations to use surrogate species to validate new biologger designs before you use them on more sensitive species. Typically, you want to place the biologger low on the animal's back behind its point of maximum girth to help reduce fluid resistance. And then probably the recommendation most akin to that mass-based recommendation for terrestrial animals is there is a general sense of keeping the biologgers, their cross-sectional area below 7% of the animal's cross-sectional area, and that, like I said, is most akin to that mass-specific recommendation for terrestrial animals. But like I said, adhering to these recommendations does present a lot of challenges for researchers. For example, we have satellite relay data loggers that need to surface to transmit data. And so those typically need to be placed high on the animal's head, which is typically a suboptimal area for drag. There are design and engineering limitations that inhibit our ability to optimize all aspects of the biologger, such as shape, density, or mass. Many of these instruments have very high power requirements based off of what type of sensors they might have, what their transmission requirements are, or how long the animal is going to carry that biologger. And then lastly, the research projects will need to deploy multiple biologgers on one animal to collect as much data as possible, with the goal both for comprehensiveness, but also to minimize the number of animals that might be needed for a study. And in addition to those multi-biologger configurations can have sort of non-trivial considerations when estimating drag. Not as straightforward. So with all of those factors to take into consideration, so how do we evaluate impacts from biologger-induced drag, particularly when we're considering these very complex configurations that are being deployed on these animals, and how do we come away with that with some confidence that their welfare is not being impacted and our data integrity is intact. And so to answer this question first, I decided to kind of venture into the world of 3D modeling and computational fluid dynamics. And so 3D models can be used to simulate drag and drag coefficient, and from there we can then validate or investigate drag proxies that we can then use on live animals or free-swimming animal data. So 3D models are pretty fantastic because they are highly sophisticated. It can be developed from 3D scans of the animals. They're very detailed, and they can be a one-to-one scale of the animal. There are many high-quality models available at little to no cost. And these 3D scans can be collected in the field using pretty accessible mobile technology like tablets, iPads, or even smartphones in some cases. And so these are two models that I helped make at Sluice of some of their sea lions, as an example. And then from there, you can use those 3D models in concert with something called computational fluid dynamics, which I'm going to refer to as CFD from here on, just for the sake of time. But these are mathematical models that use a series of governing equations that measure parameters to simulate fluid flow in a virtual environment. They are currently used in biologger development, so it's not a new concept to this idea, but they are an emergent method when applied specifically to marine mammals. There's only a handful of studies, both of these figures from each of those presented here. But they are an alternative to wind tunnels and flumes, which would be more physical models and which can be a little bit more resource intensive and complex because it's challenging to put a life-size elephant seal model in a flume and directly measure drag. So it's a great alternative to look at a variety of different biologger configurations without having to put all of that additional physical effort into it. But they can simulate drag force and drag coefficient, which drag coefficient refers to the shape of the animal or the shape of the object, so how hydrodynamic it is. And so I'll be looking at both of these for this. And then, like I said, you can generate a lot of simulated drag force and drag coefficient, and then use statistics to look at different characteristics of those biologgers and see which of those most contributes to those factors. And that will be your drag proxy. And so that leads me into, once I've evaluated those drag proxies, to then apply it to those free-swimming animals. And so that leads me to my model species, which is the northern elephant seal. And so the reason why they are a fantastic model species for this specific work is that they are very, very data-rich, and they have been deployed with a number of different biologger configurations over the last 18 plus years. So there's a wealth of different types of biologgers and different sizes, different shapes that have been used on elephant seals to collect this data. So what that means is I can compare across a bunch of different biologger configurations. And there are previous studies that have looked at how elephant seals might respond to very large biologgers from a behavioral sense. So there's a little bit of that there to kind of help guide what our predictions would be. And then they also are typically instrumented during 2 annual foraging success. They have a life history that's pretty accessible for this particular type of work. In addition to being able to compare across different biologgers, because they have these 2 annual foraging migrations, which I'm going to refer to from here on as the post-breeding and post-molt foraging trip, they have haul-out periods in which they fast in between each of these foraging trips. So in addition to making it fairly convenient to deploy these biologgers on them, it's also relatively convenient to collect data about foraging success and reproductive success that isn't necessarily tied to data from the biologgers. And then on top of that, they have a homing behavior that they almost always return to the same beach, which is pretty helpful too for getting your biologgers back and getting the same animals back. And so that is their foraging trips and when those biologgers are typically deployed. So right before the post-breeding and then retrieved right after. Then they molt and they're fasting, and right before the post-molt, and then right after when they get back. So I'll be looking at each of those. So getting into my objectives of all of this. So I'm going to first identify a drag proxy using drag force and drag coefficient derived from CFD models. And then using that drag proxy, I'm going to investigate the impact of biologger configurations on free-swimming adult female northern elephant seals from both of those foraging trips that I just talked about. And I'm going to be looking at parameters associated with dive behavior, foraging success, and reproductive success, presenting to you. And so to get a little bit further into those, To identify those drag proxies, I first split up all of those different configurations, and I wanted to look at the position of the biologger and how that influenced drag force and drag coefficient. So I separated that into head and back-mounted biologgers. And then within there, I wanted to look at number of attachment points on the head and on the back respectively, and then at the frontal area of the head-mounted and the back-mounted biologgers respectively. And then for my free-swimming animals, once I select a drag proxy from objective 1, I then want to apply it to my free-swimming animals. I had a few predictions for what I thought I might expect to see. I expected that the post-molt seals would be more vulnerable and demonstrate a greater response to drag, mainly because they typically have a lower departure mass overall, so they would have a greater proportion of added drag from those biologgers. They're also gestating, so there's an additional energetic factor. And then there's a longer exposure time, so their foraging trip is quite a bit longer than the post-breeding animals. And then for the post-breeding animals, I suspected that they would be less vulnerable to drag, have less of a response. They have a higher departure mass overall, a lower proportion of added drag. They can vary their trip durations, so if they can stay at sea longer to increase those foraging opportunities if needed, which the gestating animals can't necessarily do. And so to get into the nitty-gritty, for dive behavior, I suspected that I would see a decrease in max depth, dive duration, and bottom time due to just reduced dive capacity due to increased aerobic demand from the tags. For my trip level dive behavior, I suspected that I would see changes in the proportion or frequency of different dive types. So I suspected that they would increase the number of foraging dives and decrease the number of resting and transiting dives. And then I also wanted to look at the total number of dives, which I suspected would increase in response to drag. And then for those post-breeding animals in particular, I wanted to see if they altered their trip length at all in response to those tags. And then for foraging success and reproductive success, across both of those foraging trips, I wanted to see or suspected that they might have reduced mass gain. And then for those post-molt seals, those are the animals that are gestating, I suspected that they might have a decline in natality, so fewer births on return from their trip. But if they did have a pup, I wanted to see if the pup's mass was influenced at all, and so I suspected that the pup's mass might be reduced. All right, so how did I do all this? And so first off, I needed to get those 3D models, and I ended up using, or was able to use, some scans that were collected from elephant seals out at Año Nuevo. So these scans were collected using 3D LiDAR on an iPad Pro. And from those 3D scans that were collected in the field, I wanted to select an animal that would be a good proxy for me to kind of investigate these drag variables or biologgers with. And so what I ended up choosing was, these scans are collected before the animal departs and then after they return. I decided to use those departure scans. It's when the animal's at their lowest mass, so they're most lean. And so that was when they would be most vulnerable to drag, and that's where the data signal for this would be greatest. And so that would help me to have just a little bit greater signal to investigate. And the animal I ultimately selected was 9079, a 9-year-old female from the post-breeding trip. She had a mass that was it was roughly average for both foraging trips, and then she was a little bit on the lower end, so a little bit leaner or smaller animal. And so once again, I just felt that this animal would be the ideal one to help me find that data signal and investigate those drag proxies. So obviously that scan's pretty rough, so I had to clean it up quite a bit, and so I got rid of all that excess terrain, smoothed her out, and eliminated a few extra factors that would influence the amount of computational power I would need. So elephant seals typically swim with their flippers tucked in, so I went ahead and got rid of those extra flippers, and then simplified her rear flippers to give it a little bit more of a paddle shape. And so once I had her sorted out, I then had to build all of my biologgers. And so for these, I used computer-assisted design technology, so Autodesk Inventor Pro, and technical drawings that I bugged all of the different manufacturers for, and created all of these biologgers myself in Autodesk. I ended up creating about 21 biologgers in total that I then used to create 26 unique biologger configurations that range from 0.66 of the animal's cross-sectional area to 3.3% of the animal's cross-sectional area. And all of these biologger configurations either were used on elephant seals or are similar to ones used out on elephant seals, and I confirmed all of that via a literature review. And then lastly, the program I used was ANSYS Fluent. So this is the engineering standard for computational fluid dynamics, or CFD. It uses a 7-equation Reynolds stress model, which is pretty detailed and pretty accurate. It's relatively user-friendly, and there's a lot of detailed manuals available. I've never used this program before prior to this, so it was very helpful to dive into those resources and figure it out. But getting into what I then needed to do to create all of these models, but to use ANSYS Fluent, you have to first attach the tags to the animal, which I did in Blender, generate a wireframe, and then transfer all of that into ANSYS to actually create the fluid environment. And so that middle figure is my seal inside of a box that the computer has been told is full of seawater, and that seawater is moving in the direction of those arrows. There's an input and an output. And so once I've created what's called the geometry for this, I then move that into the next part of ANSYS Fluent to create the mesh. And all of these little polygons in there are where those equations are actually happening. And so there is the actual polygons of the mesh, and then you can see the layer around the seal is called the inflation layer, and so that's the fluid boundary where these fluid resistance calculations are occurring. And so all of that is set up so that the computer knows what it needs to do to solve these problems. And so then I had to put in all those additional parameters. So again, fluid density is going to be seawater. It's that 7-equation Reynolds stress model. I set the fluid velocity to be the equivalent of what the maximum swim speed for an elephant seal would be. Then set all the seal parameters, so the cross-sectional area of the seal at the widest point and the total length of the seal, total straight length of the seal. Solution methods, as was recommended by the previous previous paper that has done some of this type of work, and then what's recommended just from the engineering perspective. And then once all of those parameters were in, you initialize and run the model. And so each model is run for 1,000 iterations. So that's 1,000 iterations per each configuration for 26,000 total. And then from each of those 1,000 iterations, I took the mean drag and drag coefficient. And so in total, that means 26 values, 1 per each configuration. And then visually inspected, transferred all of that data into CFX Pro to visualize and inspect the pressure contours on the seal, so where there's fluid pressure and then the fluid velocity vectors, just to see what's going on. And so that brings me into methods for objective 2, which is taking all of that work done with those models and applying it to those free-swimming animals once I've identified a drag proxy. So for those free-swimming animals, I was very fortunate that I had access to 18-plus years of data. So the total number of animals I had was 256, 117 from the post-molt and 139 from the post-breeding, all adult female northern elephant seals with all those different configurations. I only used first-time deployments, so animals that had only carried biologgers for the first time. I didn't want to do any repeat deployments in case there was any impacts of behavior specific to that. We then got weights of the animals and morphometrics, so girths and lengths. Those scans were collected at departure and return. And then if it was a post-molt seal, looked at whether or not she pupped and then weighed the pup and estimated its age. And age was, or date of birth and age were estimated using daily colony surveys. All right, and then data processing for all of those biologgers. So all the time depth recorder data was processed in MATLAB using the ICNOS package. And that identifies all the individual dives, the dive phases, and the bottom wiggles that are associated with those foraging or jagged bottom dives. And then calculated dive parameters, including my dive duration, bottom time, and max depth. And then from there, all of those are fed into a dive typing algorithm, which assigns all of the different dive types that I then looked at. For my statistics, everything was performed in R with a significance value of p greater than 0.05. I evaluated multicollinearity in my linear models using variance inflation factor with threshold set to 2. And then I did my model selection using stepwise backwards selection. For those simulated drag and drag coefficient models, I used a multiple linear regression, and I selected the drag proxy based off of if that variable was significant and then what its effect size was. And so once again, those variables were the frontal area of the head and back mounted biologgers, and then the number of biologgers on the head and back. And then for my free swimming animals, I then took those drag proxies and used them as fixed effects in those models. And so those were going to be linear mixed models for dive behavior and gamma generalized linear mixed models. And so that is specified for each of those there. And then, of course, for trip level, same idea, gamma generalized linear model for those proportional dive types. And then for the number of dives for both of those trips was a linear mixed model, and then trip length for just the post-breeding animals was a linear mixed model. And then for my foraging success, I used a linear mixed model to look at mass gain. But for the reproductive success, I used a hurdle model, which evaluates that binomial, natality variable, so whether or not she had a pup using a binomial GLMM. And then if she did have a pup, looked at pup mass using a truncated Poisson GLMM. All right, and that now finally brings me to my results. And so to start out, obviously I need to figure out what those drag proxies are going to be that I'm going to be using moving forward. And so first I had to look at that drag coefficient, the results of those drag coefficient models. And I did right off the bat have a troubling little outlier, which I'm going to briefly address. But this was related to a very specific configuration that had some unique qualities about it. And so this was a configuration that had an axillary mounted biologger, so right at the seal's widest point. And so it had a much higher drag coefficient than any of the other biologger configurations that I looked at, but its drag force values were not proportionally inflated. And so what that indicated to me is that because of the location of the biologger, it significantly altered the animal shape, which led to this inflation of the drag coefficient. But these two values are calculated independently in the CFD model. And so that tells me there's some more complex variables going on that are reducing the amount of drag force that this configuration is generating relative to its drag coefficient. So for that reason, just to move forward with identifying a drag proxy, I decided to go ahead and drop this one data point from the drag coefficient model, but I retained the drag force value for this particular configuration in the drag force model. But what I suspect is happening here is a drafting effect from the head-mounted biologger that is eliminating the amount of drag that axillary biologger is creating. So that's that there. So that relatively low increase in drag can indicate a drafting effect. So looking at these two models side by side and evaluating the effect size of each of those drag proxies that I was curious about, what I ended up finding is that the frontal surface area based off of biologger configuration or biologger position has the largest effect size. So the frontal surface area of the head-mounted biologgers was the most important, and the frontal surface area of the back-mounted biologgers was the most important. They had the greatest effect size. The number of head-mounted biologgers was still relevant, but had a medium effect size, and I suspected a high likelihood of multicollinearity in the actual data set. So a lot of the same number of head-mounted biologgers with the same size. And then the number of back-mounted biologgers really wasn't that important, had small or no effect size. So what that means moving forward is that in all of my free-swimming animal models, my drag proxies are frontal surface area of the head-mounted biologgers and frontal surface area of the back-mounted biologgers. And then just showing here, I wanted to note a few of these observations when looking at the visualization of my models, because I will come back to them later in my discussion, but there are these perpendicular fluid vectors that are perpendicular to mass flow, so you can see they're pointing straight out away from the seal, whereas the other vectors are moving along the body of the seal. And this indicates lift, which could be a source of lift-induced drag. So I wanted to note those that I'll come back to in a bit. And also, you can see that there is deflection of the fluid flow away from the animal's surface, which can indicate a slipstream or a draft, which could then reduce drag, which is what I'm suspecting is happening here with that axillary-mounted biologger that I'll get into more in my discussion. But moving forward away from my CFD models into that free-swimming animal data, starting off with my dive-level dive behavior, my post-molt seals did show a significant response relative to the head-mounted biologgers, With a 4-point-fold increase in frontal surface area, there was no effect on dive duration or bottom time, but there was indicated an effect on max depth. So it seemed that their max depth was somewhat reduced by about 11.1%. And then I'm just noting that all of these values are predicted or extrapolated from the linear models as moving forward. But one thing I wanted to call attention to for this model and several of my other models is that my R-squared values are quite low. So although there is a significant effect here, only less than 1% of the variation in the data is explained by this effect, or by this variable, by the frontal surface area of the head-mounted biologgers. And so keeping that in mind moving forward, although it is significant, it seems to be a very, very small effect. But getting a little bit further into that, there was interaction with departure mass. So we did see that as departure mass increased, the effects on max depth decreased. So larger animals were predicted, or excuse me, smaller animals were predicted to have a 31% decline in max depth, whereas smaller animals were predicted to have, larger animals were predicted to have a 8.2% decline in max depth, which makes sense as larger animals would have a lower proportion of added drag from those biologgers. So for those post-breeding animals, there was a significant effect from the back-mounted biologgers, so over a 3.4-fold increase in frontal area. No effect on max depth, but there was an effect on dive duration and bottom time, with both somewhat declining. Again, these models had relatively low R-squared values, so less than 11% and less than 1% respectively explained by the model. And I did want to note that these predicted values, the 2.4 minutes and 2.2 minutes of dive duration and bottom time, are pretty similar, which indicates that the majority of the reduction in dive duration is coming from the bottom phase of the dive. All right, and so now for trip level behavior. For my post-molt animals, there was a significant effect detected for both head and back-mounted biologgers. So over those respective increases in frontal surface area, there was no effect on the number of dives, the jagged bottom and foraging dives, and transiting dives, but there was an effect on resting dives or drift dives, with it increasing with head-mounted biologgers and decreasing with back-mounted biologgers. Again, a little bit larger R-squared, but still pretty small. And then one thing I wanted to note here is that for these animals, in general, if they had large head tags, they had smaller back tags, and vice versa. So I suspect that this effect is largely due to the head-mounted biologgers, and that the back-mounted biologgers are that's just an artifact from that. But getting into those head-mounted biologgers a little bit more with these animals, there was an interaction, again, associated with departure mass. So as the frontal surface area of the head-mounted biologgers increased, those high departure mass animals tended to reduce their drift dives, whereas the low departure mass animals tended to increase their drift dives, which was interesting to note. And then for the post-breeding animals, head-mounted biologgers, as the frontal surface area increased, this was a little bit larger increase, about 5.2-fold increase in frontal surface area. No effect on the dive type or number of dives, but there was an impact on trip length. So we did see them slightly increase their trip length by about 8% or 6.3 days. And the R-squared for that model is right there. So about 12% of the variation in the data is explained by the biologgers here. But lastly, for my foraging and reproductive success, there was no effect on either of those. So there was no effect on mass gain, and there was no effect on natality or pup mass, which is great. So really exciting there. All right, so now that we're through that, that brings me to my discussion, getting into what all of this means. And I'm gonna bring you back to those CFD models one more time and get a look at what all of those mean. So first off, what we find is that frontal area is still a fantastic predictor for drag, even in these multi-biologger configurations. So that means that moving forward, we can still stick with those recommendations associated with cross-sectional area. And in particular, we can say that head-mounted biologgers are the most important when it comes to estimating drag or estimating impact of drag. Back-mounted biologgers are still kind of medium important, so we shouldn't totally disregard them. But the head ones are really what we're most interested in. And then there is some special consideration for those axillary mounted biologgers that I noted on that one particular configuration. That configuration did produce the most drag out of all the configurations I looked at, but relative to its drag coefficient was still not as much as you would expect. And they are somewhat uncommon, but I think that my results suggest that they don't need to necessarily be eliminated entirely, because there are other things to consider, which is what I'm going to get into here. So those hydrodynamic characteristics of multi-biologger configurations are what we also need to think about when looking at these drag proxies. And so first off, that drafting effect I noted with that axillary-mounted biologger, that drafting mechanic is interesting because it means that if you place the biologgers in the slipstream of the biologger in front of it, you can reduce the relative drag force associated with the drag coefficient of that particular model, which reduces the amount of individual added drag of each logger. So drafting can be really advantageous, especially in smaller animals where the biologgers are closer together, so you can really make sure you have that biologger in that slipstream. And so that means that we can use these multi-biologger configurations on smaller animals with some amount of confidence that we're reducing how much drag they're experiencing. For my free swimming animals, I couldn't find evidence of a drafting effect within their actual behavior, but I suspect it's because elephant seals are so large that the benefit of that drafting effect is reduced by how far apart the biologgers are. But we do see that in this particular configuration, there is some evidence of it being effectual for that one particular axillary-mounted biologger. And so these are those areas where that slipstream is indicated. You can see a really, really big one behind that axillary biologger, but they are behind each successive biologger. And then the next hydrodynamic characteristic I wanted to briefly address here is those perpendicular vectors indicating lift. So they're on the posterior face of the biologger, and like I said, they're pointing perpendicular to the animal, and that indicates that the fluid is moving straight away from the animal on that section. And so lift is a secondary component to drag. You can create lift-induced drag or have lift-induced drag. And what I particularly noted here is that it has a potential for premature detachment of the logger. So the loggers are effectively being peeled off from the back because they are experiencing a sort of a suction force there. So it's an area for design improvement that not only could reduce drag, but could also help retain and prevent from data loss. And then on top of that, it doesn't require you to reduce the size of the biologgers. So you can slightly alter the shape of the back of the biologger and reduce the amount of drag and reduce your potential for data loss without having to shrink anything, which is really valuable when you're talking about battery power and number of sensors and things like that. All right, so now that we've addressed all of those things with those CFD models, bringing it back to those animals. So now that we have some reasonable confidence in those drag proxies and we've applied them, what we can really take away from this is that the effect from the biologgers was pretty negligible. There were minor changes in dive behavior, but those were really the only detectable response to those tags. And although the effects are significant, less than 15%, and in some cases less than 1% of the variation of the data can be attributed to those drag proxies. So when those effects are happening, they're not happening very frequently. And there are differences between the post-molt and post-breeding animals. So I want to briefly go over those again, since I did have some predictions associated with that. So I did suspect that those post-molt animals were going to be more vulnerable due to all of these factors here. And what I ended up finding is that there were still, despite all of this, very minor effects across the range of the biologger sizes we looked at. Part of the reason why I suspected that this was the case is that overall, the post-molt seals carried smaller biologgers than the post-breeding seals. Not necessarily intentionally, but that was the case in the data set. So they already are kind of accounting for that in practice. Again, maybe not intentionally, but that's how it was in the data set. They had slightly shallower dives, which could indicate a slower gliding phase, which we can dig into more another time. And then we did have some evidence that those lower mass seals might be resting more, but overall, pretty small considering that these animals are carrying these biologgers for 9 months and they're pregnant. So very exciting. And then for those post-breeding seals, I did suspect that they would be less vulnerable for all of these reasons here. And again, we still found pretty minor effects. Although they carried a little bit larger biologgers, I suspect that there's only a small number of larger biologgers that might be driving those effects. So possibly those axillary-mounted biologgers, which did indicate those animals did indicate a little bit of reduced bottom time, which could suggest increased aerobic demand. And then they did spend a little bit more time at sea, potentially. But again, keeping in mind that the R-squared value on all of those models is pretty small. So again, very minor effects. And so, conclusion. What we can all take away from this is that both post-molt and post-breeding seals have pretty low-effort swim styles. So they have a gliding phase that they use for a lot of their dives. And from previous work, we know that activity level correlates to the amount of applied force that these animals are getting from biologgers. And so because of that low-effort swim style, I suspect that that means that they're already sort of minimizing the amount of drag that they're experiencing. Makes sense? And so what that means is that there are no long-term effects from these biologgers. So, yay. And so the key takeaways are that the frontal surface area remains a really good proxy for drag even with multiple biologgers. Shape and position is still pretty relevant, but we can take advantage of that to take advantage of those drafting effects on smaller species, and then we can address lift as a potential area for drag and data loss. But if we minimize both of those, the largest configuration I looked at here was about 3.3% of the animal's cross-sectional area. So if we keep it below that, then we shouldn't see any effect, if at all. And then lastly, CFD is a really great tool to optimize biologger design and placement and evaluate biologger configurations before you even have to deploy them on the animal. So it's a really great thing that we can look into further as an option for this. All right, and now for my acknowledgements. So first off, thank you to my thesis committee for helping me get through all of this data and all of the complexities with this. There was a lot of nuance to dig through and a lot of stat models to understand and terminology that I still don't quite totally have down, but I'm getting there. And so thank you all so much for that guidance. This is my funding sources, so thank you to the Año Nuevo Research Project and members of the Costa and Beltran Lab for entrusting me with 20 years worth of data of over 200 plus animals. It's quite a privilege there, so thank you so much for all of that. To the Vertebrate Ecology Lab for just being a really fantastic environment to learn and grow in, and for sharing their knowledge and helping me create a community, even though, as Gita noted, I will just hobbit away if left to my own devices. So thank you so much. And then, of course, to so many more people who supported me through all of this, to the Hoffa Lab, who are where I got my start in the SLUIS project for really helping me grow and gain confidence in switching to a new field. And then, of course, to my family and so many more for supporting me in this career, and to my dad for saying it was really about time when I told him that I applied for this program. He was like, you took long enough. And then not to end it on a little bit of a somber note, but I did want to say that this is in memory of some people who couldn't be here, who didn't quite make it through, but sorry, I didn't think I would choke up at this point, but thank you to these folks. May we meet again somewhere on the seashore. All right. Any questions? Yeah. So fluid velocity is a direct component of drag. So as fluid velocity increases, drag force increases. And so again, with those CFD models, what I was trying to replicate was basically worst case scenario. So smallish animal, at least that was still within the standard deviation of what you would put tags on. And then, what scenario would that animal be experiencing the largest amount of possible drag force? So that would be when the animal is swimming its hardest. So maximum swim speed, which for an elephant seal, what I found was 5 meters per second, which really is like pretty fast. And so that's what I set that at, just to make sure I got as big of a signal as possible for those computational fluid dynamics models that I could then use to parse out what characteristic was contributing the most to that signal.
Cool, awesome, thanks.
Oh.
Thanks, Bruno. Okay, great presentation. This was an insane amount of work. I do have kind of a niche question. At the beginning of your presentation, you had some 3D models of sea lions from sleuths data, and I know that adult male sea lions kind of form a little crest in their forehead, and I know this is female elephant seals, but I was wondering if you saw any reduction of drag because of slipstreams because of different morphologies.
I didn't see that because for those sea lion models, I didn't do drag on those. And then for the elephant seals, I only looked at one animal. So there was no comparison between different animals of different sizes. I would have been here for another 5 years if I did that. But I did consider that. I actually, at the beginning, I had two animals. I had one from the post-molt and one from the post-breeding. And what led me to narrow in on this smaller animal is that the larger animal from the it happened to be that the larger animal was from the post-molt trip, even though that's not what it typically is. But that larger animal had a lot muddier computational fluid dynamics data because there just wasn't as big of a signal. And so, yeah, different morphologies just based off of that preliminary look at it does impact how much drag the animal's experiencing, which is why I went with a smaller animal model.
Thank you.
Awesome presentation, Kaylee. So there was some lift that happened with some of the tags. Was there any shapes of the tags that you noticed that didn't have much lift off the back?
So I mainly focused on the ones that had the most. I didn't quantify lift. So I only looked at the actual visualization of the models. I believe you can go into ANSYS Fluent and actually quantify that. But per your question, if I actually go back, because I might have an image in here somewhere. So you can kind of see it on this one, but the color of the arrow indicates how fast the fluid is going. So if you look at that axillary-mounted biologger, those arrows are dark blue, and then on the sprue tag on the front, they're a lighter blue. So the lighter the color for this particular one indicates it's going a little bit faster. So that axillary-mounted biologger has less lift, at least going from visual interpretation, than that sprue tag. So that's one way to evaluate it, and there is a difference, of course. But for this one, of course, there's that drafting effect happening, which is going to influence how much lift force is happening as well, because how much fluid is hitting the tag. But for shapes, I didn't get a chance to model it, but generally the more sloped the tag is on the back, the less lift you're going to have, because there's less turbulence happening back there. So that is kind of the shape that you're looking for, is something that's a little bit more tapered and sloped. The VHF tags had very little lift that I could see, but they're also a lot smaller, and they have a much smaller face on the back. So hopefully that somewhat answers it. That's something I wanted to do that I didn't get to do. Yeah, more rounded, more tapered. Yeah, teardrop, torpedo, all of those things.
That would be fun to play around with to see if you could create one that has.
I had someone offer to 3D print something for me.